You may not regularly fly into airports where you see a lot of airliners. But now and then, when you're flying IFR, you may choose one of those airports for your destination, just because those airports have better approaches with lower minimums. However, along with the benefit of all those facilities and better approaches, you also get a hazard that you don't often see at general aviation airports. That hazard is wake turbulence, those horizontal tornadoes which trail from the wingtips of big airplanes. Let's review for a minute what we know about wake turbulence. First, let's look at a boat going through the water. Now notice the wake that it's generating. Well, an airplane also generates a wake in the air. We call that wake turbulence or wingtip vortices. Wingtip vortices occur because anytime an airplane is flying, there's a high pressure underneath the wing and a low pressure area on top of the wing. So the air from underneath the wing tries to make its way around the wingtip and join that low pressure area on top of the wing. The problem is that by the time these molecules make their way around the wingtip, the wing is gone. It isn't there anymore. So what you really get are these wingtip vortices following the aircraft like horizontal tornadoes. Anytime an aircraft is producing lift, you'll have these wingtip vortices. And they are strongest when the airplane is at high angles of attack, namely when the airplane is heavy or slow, such as just after takeoff. Now, these vortices are a danger to you when you are flying in a little airplane and you're following a bigger airplane because they can roll you upside down. Now, if you're flying at 2,000 feet and you get caught in a wake turbulence and do an inadvertent roll, it scares the daylights out of you. But at 50 feet above the ground on short final, it can ruin your whole doggone day. So the important thing to know is how these vortices work. First of all, they occur anytime there is lift on the wings. They start when the nose wheel of the airplane leaves the ground, and they stay until the nose wheel returns to the ground. Next, they tend to sink behind the airplane. If you want to avoid the vortices of a big airplane, you would want to fly above the flight path of the aircraft that's generating the wake turbulence. Also, you need to know that when the vortices get near the ground, they tend to spread apart and drift with the wind. And the one condition that requires maximum caution when you're avoiding wake turbulence is a light quartering tailwind. Now here's why. Let's assume that these vortices drift apart at a rate of 5 knots. And let's assume that you have a 5-knot quartering tailwind. Well, you could see what would happen. This upwind vortex would be held right over the runway. The downwind vortex would be blown away, and that's no problem. So when you have a light quartering tailwind, the upwind vortex could be right here over the runway, and that would be your most dangerous situation. Not only is a light quartering tailwind a wake turbulence hazard, but any crosswind up to about 7 knots can have the same effect of keeping the upwind vortex over the runway. So watch out for any light crosswind component when wake turbulence is a consideration. Now let's assume that you're landing behind a bigger aircraft. What should you do? Well, what you should do is fly above the landing aircraft's flight path. Because the vortices are generated right here, they sink below the aircraft's flight path. So on a precision approach, you'll want to be on glide slope or slightly above, but never below. But what if you don't have a glide slope to follow? Then the aim suggests that you fly on or above an approximate 3-degree glide path. Now you can estimate this by using what we call the 3-to-1 principle. The 3-to-1 principle means that you should take your distance from the runway in miles and multiply by 3 to find the altitude you should be at in hundreds of feet. In other words, when you are, let's say 5 miles out, you should be at 1,500 feet above ground level. At 4 miles, 1,200 feet, and so on, as long as these altitudes are above the MDA. Now, when you land, you want to land beyond the point where the airliner's nose wheel touches the ground, because lift is generated by the wings until the nose wheel touches the ground. And since in IFR conditions you probably didn't see his touchdown point, make your touchdown a little beyond the touchdown zone markings, or where you see all the tire marks on the runway. Now, a hazard that goes hand in hand with IFR flying is hydroplaning due to wet runways. As you know, what happens when you're hydroplaning is that a thin film of water actually separates your tires from the runway surface, reducing your braking action to nothing. It's like you're sliding on ice. You have very little, if any, directional control or braking ability. You can expect hydroplaning when you are at high speeds and when there's standing water or slush on the runway, especially if it's a smooth runway. So if you see water on the runway, touch down at a slow speed. And if the runway is long enough, let your airplane slow down significantly before you use your brakes. If you don't have the luxury of a long runway, lower your nose to the runway as soon as possible after touchdown to get more weight on the main wheels and to gain the help of the nose wheel for directional control. Also, it helps to raise your flaps to put even more weight on your wheels. But if you're flying an airplane with retractable gear, make sure you have the flap handle, not the gear handle, in your hand. Otherwise, it'll take full power to taxi off the runway. And finally, make sure you continue to use your best crosswind correction technique after touchdown. Wake turbulence and hydroplaning aren't unique to IFR flying. However, you're likely to see them more frequently in IFR conditions. Now that you're aware of the special hazard they present to IFR pilots, you'll be armed to deal with them successfully.